What follows here are the other type of major reaction involving alkynes, and it involves addition reactions to the carbon-carbon triple bond. These are, in many cases, very similar to what was back in chapter 6 of your book, where the addition to alkenes was dealt with, where you started off with a double bond. And so, again, with triple bonds, much of the same, and just as I do with alkenes, that the starting point is the simple hydrogenation, adding pairs of hydrogen atoms across triple bonds, and if you add 2 equivalents of hydrogen for each molecule of the alkyne, then you turn that alkyne into the corresponding alkane. So it has the 4 new hydrogens, and just as was the case with alkenes, the catalysts here involve these expensive types of metals: PT's platinum, palladium, well, I guess nickel's not all that expensive, rhodium is RH, and these would be powdered metals exposed to the alkynes, which are oftentimes in the gas phase, and certainly the hydrogen gas is as well, but the reaction takes place on the surface of these metal catalysts and can be done in very quick fashion. Now you can control the amount of hydrogen you're using so that at the bottom here, if you only have 1 equivalent of hydrogen instead of the 2 equivalents, then you just add 2 atoms of hydrogen instead of adding 4 atoms. Now in this case, if your alkyne here is one in which the triple bond's in the middle of a chain, where the R groups would be methyls or ethyls, things like that, then you have the possibility of making an either a cis or a trans alkene. What this shows is the recipe that produces predominantly the cis isomer. Lindlar's palladium is what's indicated here. It's a palladium metal along with a few other ingredients, but the thing to know is just that that recipe indicates that you do add hydrogen across that double bond, but that you turn the alkyne into the corresponding cis isomer of the alkene. And it's nice to have that kind of control, because in this next slide we can do the opposite if we use a different recipe. That is, we can make the trans alkene starting from the same alkyne. This is involving sodium or lithium metal that would be mixed in with liquid ammonia. So just like the acetylide reactions I talked about, this takes place not in something simple like water or an alcohol, but rather in a chill down liquid ammonia solvent system. And so the idea is that this results in the corresponding trans isomer. And we're not going to worry too much about the intricacies of the mechanism of this, but you do need to be familiar with the 2 recipes in which one produces cis and which one produces trans. This also kind of harkens back to the alkene chapters. There was this thing called Markovnikovs rule, where when you add something across a multiple bond like HCl or HBr, where it's not identical atoms, then you have the sometimes problem of deciding, well, to which carbon does the hydrogen add and to which carbon does the halogen add. And Markovnikovs rule says that whichever one of the carbons has the most hydrogens, that's where the incoming hydrogen goes. So this first carbon already has a hydrogen. The second one maybe has a methyl or ethyl group, so 0 hydrogens. So it's showing that incoming H turning the CH into CH2, which therefore puts the halogen in the on the other carbon. So that rule is generally followed, and you can continue that if you add more of the corresponding halogen. Markovnikovs rule happens again. So notice in this reaction down below, the CH2 turns into a CH3. Our double bond is now a single bond, and we end up with 2 halogens on the same atom. And this term geminal refers to that relationship. When you have 2 halogens or 2 of anything on one carbon, we say they have a geminal relationship, as opposed to if the halogens were on adjacent carbons, in which case the term is vicinal. I guess they're in the vicinity of each other, but not exactly on the same carbon. Geminal kind of comes from Gemini, the twins, so I guess these are twin halogens. And so depending on where you want your halogens to be, this kind of offers a way to control that. And then related to that is putting the halogens on 2 at a time. So just like we can add H2, we can also add Cl2 or Br2. We usually don't use the corresponding F2 for fluorine because F2 is extremely unstable and downright explosive. And I2 iodines don't tend to react as easily. So chlorine and bromine are used a lot. And if we are adding 2 equivalents, then we end up with a single bond, so there's no cis or trans to deal with there. And notice we end up with 4 halogens. I guess 2 pairs of geminal attachments, if you will. If you limit the amount of the halogen, so notice down at the bottom the difference is just 1 molecule of X2 versus 2, then you can stop at the stage of just putting 2 new atoms in the molecule. And notice here we don't have any control over it being cis or trans. It will always be trans. The halogens always end up in a trans relationship to one another. So that, again, is something to pay attention to.